they also tell you this, okay? So the density of the planet is the mass of the planet divided by the volume of the planet cubed. That's twice the density of Earth. Okay, so this equation tells you, the second equation tells you okay, that's so we'll call this equation 2. Now let's copy this. Okay, so from here, this tells you MP over RP square equal to 2 times ME over RE square times RP over RE. What did I do? I took one RP over here and put it there and separated one RE over there. Okay. And the reason I did that is, see, this guy I can replace with that. So 3 times ME. So substituting 1 in 2, 3 times ME RE square equal to 2 times ME so RP by RE. So the radius of the planet is 1.5 times that the radius of the Earth. Yep.
Why are you writing on just the radius instead of like the volume?
What do you mean?
Because
No, here's the volume and these cancel.
Oh, okay. Are you just trying to find like the scale factor?
Yeah, the scale factor. So, what is the escape speed of the satellite located at Moon's orbit about Earth? Assume Moon is not nearby. Okay. So, the escape velocity there. You saw that the escape velocity from any is 2gm divided by r. R is how far you are away. Okay, so the further away you are, the smaller the escape velocity. Okay. So you can see that the moon is really, we are bound to the sun. The moon is okay. All right, so the escape velocity from that distance. Okay, guys, so let's calculate this. What is the gravitational constant? Gravitational constant. Okay, so the mass of the Earth is 10 to the 24 kgs, and Earth-Moon distance. .84 into 10 to the power 8 meters. Okay, so the escape velocity at that distance is, you take care of powers of 10. This is 10 to the power 16, and that gives you 10 to the power 5. So we'll make it 20 times 6.67 into 10 to the 2 meters per second. So the escape velocity from Earth's gravity near at the moon distance is 0.6 kilometers a second. Okay. From the surface of the Earth, it's 11 kilometers a second. Okay. This problem says an average-sized asteroid located 5 times 10 to the 7 kilometers from the Earth with a mass of 2 times 10 to the 3 kgs is detected headed directly toward Earth with a speed of 2 kilometers per second. What will its speed be just before it hits our atmosphere? Okay, so yeah. So, the dinosaurs were supposed to have been wiped out by an asteroid hitting the Earth, and then all the dust that enveloped the Earth made it dark for several years, and that's what killed out a lot of life back then. All right, so what we're going to do is we'll use conservation of energy. The kinetic energy initial plus initial potential energy No, our final will be you're close to the surface of the Earth, so we'll just use the radius of the Earth. All right. You can see that this mass cancels. So the mass of the asteroid is not relevant. All asteroids would hit at the same speed if they were going at that speed. So we're calculating the final speed. V final square is equal to V initial square plus G M by R final minus R initial. Okay. Oh, then we multiply the whole thing by 2. So this is 2 times 2 times. So R final is the radius of the Earth. The radius of the Earth is 6,400 kilometers, which is 6.4 into 10 to the 6 meters minus 150 into 10 to the 6 meters. So you see, this number is 10 times bigger than that number. So this number is about 1/10 of this number. So we can sort of throw that away. Okay, you can calculate it accurately if you want, but I'm just going to show you a quick calculation. All right, so actually, why not? We'll calculate it. So V final in gravity, this everything gets messy. 6.4 into 10 to the power 6 minus 1. Okay, so 2 kilometers. Mass of the Earth is 6 into 10 to the power 24, then times okay, so that's 10 to the minus 17, 10 to the plus 7. Okay, so this is 4 into 10 to the power 6 plus 2 into 6.67 into 6 into 1 over 6.4 minus 1 over 50. And what did we say? Into 10 to the power 7. Okay, so you see that so the initial speed was 2 kilometers per second. Gravitational potential energy got converted to kinetic energy. So most of the energy was from that. So this is almost negligible. Okay. So the final velocity is works out to 10.6 kilometers a second. Okay. And that'll deposit a lot of energy when it collides with Earth. Okay, so compare this energy to the output of the largest fission bombs, which is 21 terajoules. Okay, so the largest atom bomb. Um, so so kinetic energy plus energy of the bomb, 1/2 mv squared divided by. And now we'll use the mass of the asteroid, 2 times 10 to the 13. The velocity is 10.6 kilometers meters per second. So this tells us this is the energy of the asteroid hitting, and this is the energy of a bomb. So how many bombs is it equivalent to? Okay. So that's 10 to the 12, that's 6, 10 to the 19. So 10.6 square into 10 to the 19 joules. Divided by. Okay, that's 12, 15, 4. So 10.6. Half a million bombs. Okay. That one asteroid hitting the Earth would be like exploding the 500,000 of the largest atom bombs. Okay, I'll solve 2 more problems. Let's do this one. So this is, what would be the Schwarzschild radius in light years if our Milky Way galaxy of 100 billion stars, okay, well, it's more than that, but anyway, collapsed into a black hole. So what this is if we turn our galaxy into a black hole, what would be the size of the black hole is the question. Okay. We have more like 800 billion stars, but anyway, compare this to our distance from the center, about 1300 light years. Okay, so here's the Milky Way galaxy. We are about 1300 light years. What we're going to do is we're going to turn this galaxy into a black hole and see how big it will become. Okay? 'C is the speed of light. So that would be the size of the black hole. That's the gravitational constant. This is the mass of our galaxy. Okay? 10 to the minus 11. 100 billion, that's 10 to the 11. When they say stars, what they mean is, so this is what's implied. They're saying solar masses, okay? So, and the mass of our sun is 2 times 10 to the 30 kgs. What is the speed of light? Okay, that's the speed of light. All right, so now let's take care of powers of 10. 30, 41, oh, this canceled that, that's convenient. 30 divided by 30 minus 16 is 14, so 10 to the 14. And this is coming out in meters, 2 into 6.67 into 2, there's a 2 here, divided by 9. That would be the Schwarzschild radius. Light year in meters. Okay, so 1 light year in meters is 9.5. So the Schwarzschild radius would be .03 light years. So that's let's convert that into more convenient light days. So that's how long it would take light to travel from the center to, that would be the size of it. Okay. All right, I guess we'll